Good afternoon, everyone. Welcome to the Tutte Colloquium. Very happy to have Sophie Spirkl speaking today. Thanks, everyone, for wearing masks. Helping keep the COVID spread low. So Sophie is a Canada Research Chair in Graph Structure and Algorithms and a professor here in our department who works on graph structure and algorithms. So she was before Waterloo, was an NSF postdoc at Princeton and also at Rutgers, and received her PhD from Princeton. So please, the floor is yours.
All right, thank you so much. First of all, can everyone hear me okay? I know that sometimes with the mask it's a bit difficult, so if at any point I slip, please remind me. But yeah, thank you so much for coming. I see that there's a non-empty intersection with people who are taking my class, so those of you who are also in my class will hear a much, much longer version of this talk as the term progresses, but you can use this as a little preview of what's to come. So yeah, I want to tell you a few things about tournaments, and I'll try to tell you basically a bunch of different things that I find interesting in the hopes that maybe you'll find some of them interesting as well. And if none of the words mean anything to you, I will try to tell you what they mean as we go. Do interrupt if you have questions. Oh, and I'm supposed to update this with the Canada Research Chair thing. It's a secret, but I'm supposed to also tell everybody. I don't know how it works. At some point I will find out. Okay, so a tournament is a special kind of graph. In a normal graph, we have edges and non-edges, and a tournament is kind of like that in that there are two options. For every pair of vertices, you either have an edge going this way or an edge going the other way, never both, and never neither. And if you think about it, that's horrible. If you picture a 100-vertex graph and they're all pairwise adjacent, you will get absolutely no idea what's going on. So usually when we think about tournaments, it's more convenient to think about the back-edge graph. And I'm saying the back-edge graph, which is also a lie. If you have a tournament and you take its vertices and put them in some order, then the back-edge graph means you forget about all the edges that go left to right. You draw the ones that go right to left. You don't need to draw the orientation anymore because the edges you've drawn go right to left. The other pairs are adjacent, left to right. I'm terrible at left and right, so if I mess it up, you can fill it in yourself. But right in this tournament, we have vertices 1, 2, 3, 4, and all edges go from smaller number to bigger number, except that 4 points to 1, which is bigger number to smaller. And so in the back-edge graph, that's the only edge I've drawn. Now, the lie about this is that that's not unique, right? I numbered the vertices 1, 2, 3, 4, but if I had picked different labels for the vertices, we would have gotten a different ordering and a different back-edge graph. So in general, back-edge graphs are nice when you're thinking about tournaments, but they're not unique, and that's kind of where a lot of the difficulty lies. When you start thinking about graphs, you might first, if you're trying to go for graph structures, say, what's the most structured graph? If you wanted to give me a graph that you understand the absolute best, what would it look like? I'm teaching this term, so I'm expecting people to respond. It's true, the simplest possible thing is if they all go in the same direction, which kind of corresponds to the simplest possible undirected graph as the back-edge graph, which is no edges. And that's called a transitive tournament because if you look at what the edges are doing, they have the transitive property. If you have this one, you also have that one. And they are kind of the most basic building block that you can have in a tournament. And a transitive tournament can be characterized in a number of ways. Kind of probably the first that makes most sense is just edges go left to right. But also in the back-edge graph, it's nice to think of it as the back edge graph, if you put it in the correct order, doesn't have any edges, and so it sort of acts like a stable set in a graph. It's also true that transitive tournaments are the only tournaments that don't have directed cycles, and so that's another characterization. And now that I've showed you what a stable set is, the next thing we were going to do with it is coloring. And this is actually a notion of coloring that was defined for all directed graphs. In general, in a directed graph, it says we want each color class to be acyclic, to have no directed cycle. But in a tournament, it's even easier. Equivalently, it means each color class is a transitive tournament. And color class means vertices that get the same color, right? So if I look at this 4-vertex tournament, the red and blue coloring is a coloring, because if you look at 1 and 3, well, that's only 2 vertices, so there's certainly not going to be a cycle. And the same for 2 and 4. And it sort of makes sense that this is more sensible in tournaments than regular coloring, where, right, if you do the usual coloring, each vertex will get its own color. Nice, but that's boring. And so this is more exciting, because now you can ask all sorts of questions. The first, which is kind of easy, is this lemma. If you think about what does this type of coloring mean in the back edge graph, well, that depends on which back edge graph you choose. But one thing you can do is you can say, I'm going to choose my back edge graph where I take all the red vertices and put them in the order that doesn't give me any edges between them, because they're transitive tournament. And then I'm going to take all the blue vertices and put them in the order that doesn't give me edges between blue vertices, and so on. When you do this, you construct a back edge graph which is properly colored in the normal graph sense by the coloring of the tournament. And the converse. If you have a back edge graph and a proper coloring in the normal graph sense of coloring of that back edge graph, each color class is stable in the back edge graph and hence transitive in the tournament. So a coloring of the tournament gives you a coloring of some back edge graph, and every coloring of every back edge graph gives you a coloring of the tournament. Said differently, we could define chromatic number of a tournament as look at all back edge graphs, look at the smallest chromatic number of any of them, which is one way that people define things for tournaments. But finding the right back edge graph is hard. And for tournaments, here's one way to see that. If I give you a graph and ask you to two-color it, and you've taken RT8 Math 239, then you know what to do. If I give you a tournament and I ask you to two-color it, we're in trouble. What does two-coloring mean? Well, if you think about it, a transitive tournament means that you don't have any directed triangle, and those two are equivalent. So really, if you think about what we're doing when two-coloring a tournament, is we're looking at all the directed triangles, and we're trying to make sure none of them end up monochromatic. This looks a lot like we're two-coloring a 3-uniform hypergraph, which is NP-hard. And it turns out that basically that idea you can take and adapt directly to show that two-coloring tournaments is NP-complete. But it's annoying, right? Two-coloring graphs is so easy we don't even think about it, and two-coloring tournaments already impossible. I'm not going to show you the full reduction because I don't think anybody is prepared on a Friday afternoon to do a full NP-hardness reduction, but I'll show you one idea, and the one idea is this gadget. If you look at this gadget, then in every two-coloring, U and V have to get different colors. Because if you color U and V both blue, look at any of the vertices in between U and V. All of them actually form a cyclic triangle with U and V. because it goes U to the guy in the middle, to V, and back. So if U and V are both blue, the guys in the middle are all red, but the guys in the middle are also a cyclic triangle, and you've lost. So somehow, this gadget is a way to say, I want U and V to actually have different colors, which allows you to propagate information in your NP hardness reduction. And that's the main idea. Then you stick it together like this. But I'm going to be nice to you and just pretend that I didn't make that slide. If you know me, you know the next question I ask, which is, fine, so this is hard. What if I exclude some tournament? What if I say, okay, here's a tournament H, now let's two-color H-free tournaments? And wouldn't it be nice if there was a pretty answer for this? But at the moment, we don't even have a conjecture for what the answer should be. And by the answer, I mean, given the tournament you exclude, when is it easy and when is it NP hard? It'd be nice to say it's easy if the tournament looks like this, and it's hard in all the other cases. But at the moment, we know it's easy if the tournament you exclude has a back edge graph with only one back edge, which doesn't sound very impressive in the grand scheme of things, but is already non-trivial. And the reduction I showed you can be messed with in various ways to show that, well, the thing you're excluding does have to have a back edge graph which is pretty sparse, which makes sense, right? If every back edge graph is dense, then that's a thing that's not very relevant to coloring. So you need to have a back edge graph that satisfies all the words that are written here. And, well, if the world was nice, this would at least be analogous to what happens when we're saying three-coloring graphs is NP hard. What if I forbid an induced subgraph? But there we have a conjectured answer. There the conjectured answer is, if you exclude anything that's an induced subgraph of a path, then three-coloring should be easy, and in any other case it should be hard. That's nice. That's at least a pretty conjecture, even though nobody can prove it. For tournaments, homework 1 for this See It's Teaching Mode class is conjecture an answer for this that is at least a little bit pretty. Apart from the two things I showed you, right, it's easy if you exclude something with only one back edge. It's hard if a bunch of words that don't give a very pretty answer. All the other cases where we know something come from just saying, if I exclude that thing, my whole tournament has a structure, which is super nice. So let me tell you what we know in this direction, because it is not very much. Right, but that's something you could try to do. You could try to say, here's this small tournament, if I exclude this, maybe there's a nice recipe to make all tournaments that don't contain this little thing. That's something that exists in graphs for some small cases as well, and it gives you nice answers in some of the cases. For tournaments, here's what we know. This is the easiest if you exclude this, which, remember, that's just a cyclic triangle. Then you get a transitive tournament. Good. That is not a very impressive structure theorem. So let's be a bit more ambitious. If you exclude this, which is also the graph from the first slide, then we actually still get very close structure, because this is the only four-vertex strongly connected tournament. In other words, if you exclude this, each strongly connected component has size at most 3, because as soon as you make a bigger strong component, you're going to contain this one. And from there, things get a bit more complicated, and I am lying about each of them, but not by, I think, an important part. First, there's this, which is a vertex that's out adjacent to a cyclic triangle, which again doesn't seem overly ambitious because that's a 4-vertex tournament and there's only one back edge. But the result is already not trivial, and the answer you get is this. And by this, I mean the structure is basically you put a bunch of vertices on a circle, like an actual unit circle, and then you orient the edges clockwise, meaning if 2 vertices are on your circle somewhere, the edge between them goes in the direction of the shorter clockwise circle segment. And this seems to be a fundamental tournament. It kind of shows up in a lot of these structure theorems. I don't know what it means, but it somehow seems to be one of the basic kinds of tournaments. If we go a bit further and exclude this thing, the answer doesn't change too much. You once again get our friend Tn, and then you get another tournament which seems to be fundamental, and yes, yet it's even less clear why, which is the tournament you get from Tn by saying, now let's pick half of it and reverse all the edges in there. Why would that be fundamental? I don't know, but it seems to be. So there's this Tn thing, which is clockwise, and that one at least is very symmetrical and pretty. And there's Un, where we take that and then take all the edges that live within one side and just say flip them. I promise the rest of this is not just, here are all the structure theorems. I know it ends on this slide.
Wait, can I ask a stupid question?
Yes.
The one where you flip it, why does it have 2 parameters? Because the size of the part you flip.
That's a great question. It's because you're supposed to flip exactly half, except it has an odd number of vertices. You flip half minus 1. But yeah, that's a very good question. The other things that you say, I think you get by the a bit part that I lied about, which is that you can turn one vertex into multiple by blowing it up. So for the version where I'm lying, you only need the half. I'm going to ramble at you about structure theorems a bit more because I think it's fun to see what basic tournaments fall out. Right? For graphs, we kind of have a notion of what are easy graphs. Maybe paths, cycles, trees, bipartite graphs. We at least have a notion of these are the kinds of graphs everybody should know about. For tournaments, there's transitive tournaments. And so maybe these are the answers, but we don't actually know. The next one is my guess as to what a bipartite tournament should be. In a bipartite graph, right, every edge goes between the 2 parts. And this structure, which is totally clear from the picture, I imagine, is a tournament where you have 3 parts, and every cyclic triangle hits all 3 parts. And so it kind of makes sense that then sounds like a bipartite graph, right? It's bipartite graph, every edge hits both parts, and this one you have 3 parts, and every cyclic triangle, which is sort of the analog of an edge, hits all 3. And again, this falls out as the structure of some tournaments naturally. And then I have to advertise for the local result, which is if you exclude this one tournament, then you basically get a back edge graph that's just a disjoint union of paths. Which is also strange. That doesn't immediately seem like that should be a basic kind of tournament, but maybe it is. If you enjoyed this story about what are basic tournaments, I don't know. Here are the next 2 tasks on this list. Both of them seem quite hard. I recommend this one, if you do go for one. But yeah, somehow That's it. That's the cases where we actually know what the structure looks like. And I mean, some of that is fair, right? In graphs, we also don't have too many structure theorems for forbidding an induced subgraph. But I think from this, it's still not very clear what are the simple tournaments that we completely understand. Let's therefore move on to what can we say. And so if somehow the complexity of coloring when forbidding something basically remains a mystery in many cases, let's try the other thing. What if I just want you exclude something and now chromatic number is bounded? That's not really interesting in graphs, because the only thing that works is if you exclude an edge or a vertex. Anything else, you're in trouble. And so for graphs, you exclude one thing. Chromatic number is bounded question, not very interesting. Exclude two things, chromatic number is bounded, is a very interesting question. But for tournaments, even excluding one thing turns out to have a non-trivial answer, and this is, I think, possibly the most well-known result on tournaments and structure. It says, if you just exclude one tournament, this gives you bounded chromatic number if and only if that tournament is a so-called hero. And a hero is a tournament that is defined inductively using these operations. Right, the first is a single vertex is a hero. Certainly, if you exclude one vertex, then there's no tournament left. And then there are two other operations. You can take two tournaments that are heroes and make all edges between them go this direction. You get another hero. Or this mystery operation where you say, I'm going to put one vertex here, and then in one of these two spots I'm going to put a hero, the other is a transitive tournament, and then I'm making the whole thing look like a triangle. And this is an exact answer. If you exclude one thing, you get bounded chromatic number if and only if it's one of these things. Which is a really nice result. But there's something a tiny bit annoying about it, which is that heroes have chromatic number 2. So they're not actually telling you, oh yeah, this has big chromatic number. It lives here in this hero. It's just, if you exclude this, you get bounded chromatic number. If not, there's some construction that has large chromatic number, but the heroes are not really, here's the cause of large chromatic number. This is where it comes from. They're all two colorable. And actually, I haven't yet shown you an example of a tournament that is not two colorable. So perhaps this would be a good thing to address at some point. Are all tournaments two colorable? They're not. And I mean, if you make a random tournament with probability 1/2, that's going to have huge chromatic number, but let's be a bit more deterministic. And so here's a construction for making tournaments with huge chromatic number. It looks a lot like the construction for heroes, which is certainly no accident, because heroes definitely need to get rid of this construction. You start with a single vertex, and then once you have made the graph dn-1, the previous one in the sequence, to get the next one, you take one vertex, a copy of dn-1, a copy of dn-1, and you put them in a triangle. And by put them in a triangle, I mean you make all of these edges go this way, all of these go this way, all of these go that way. Why does this have large chromatic number? Well, let's prove that it needs n colors inductively. Then each of these two bubbles needs n-1 colors. And if that set of n-1 is not the same set here and there, then their union has size at least n, and we're done. So you can assume the same n-1 colors show up here and there. But then, if one of those colors also shows up here, you can immediately construct a cyclic triangle that's all the same color by taking the vertex on top, somebody of that color here, and somebody of that color there. So if you use the same n-1 colors here and there, then the vertex on top is going to need a new color. And once again, we've used n colors. So this is your possibly first example of, yes, actually tournaments can have chromatic number larger than 2. It would be nice if this was the only way, but then we could say, well, every tournament with large chromatic number contains this. And that would be too easy. Let's look at another one. This one is fun because it very much looks like a complete graph, which, right, if I ask you, tell me a graph with large chromatic number, you might first say complete graph. That's an example. And so this is sort of like that. Again, it's defined inductively. A1 is a single vertex. And then to make an, what you do is, this is a picture in terms of the back edge graph. So you take a complete graph on n vertices, and then between every 2 vertices, you put a copy of an minus 1. And in the back edge graph, it has no edges to anything else, which means in the actual tournament, all the edges from here go this way, and from here go that way, and from here go that way, but I was too lazy to draw them all. But right, if you think of the back edge graph of an inductively, it's just a bunch of complete graphs that are interleaving in kind of funny ways. And because it's not too hard, let me tell you why this has large chromatic number. If you think about it, each of these edges, together with any vertex in this an minus 1, is a cyclic triangle. And so that will be the main driver of why does this have large chromatic number. We have these n vertices on top in the complete graph that suspiciously match the number n in an. So let's think about what would happen if we colored this tournament with fewer than n colors. Then there would be 2 vertices up here that get the same color. I don't know that they're consecutive. It might be the first and the last. It doesn't matter. But there are 2 vertices in that big complete graph that get the same color. And there is at least 1 copy of an minus 1 between them. Maybe there's multiple, doesn't matter. Well, then in this copy of an minus 1, I better not use that color that's shared by these 2 vertices, or exactly this cyclic triangle will end up all of the same color. So in this copy of an minus 1, I need n minus 1 colors by induction. And then there's the one more that appears on that edge, but not in an minus 1. And so this, again, is a tournament with chromatic number n. And n is also an upper bound if you think about it, because the back edge graph is a disjoint union of cliques all of size at most n. So we actually have an exact answer. All right, you say, this is sort of promising. Maybe that's the truth then. If a tournament has large chromatic number, it's an or it's dn. That would be nice. It's also not true. But to tell you why it's not true, let's talk a bit more about back edge graphs. I told you that a transitive tournament is a tournament which has a back edge graph that has no edges. But sometimes you're not that lucky. Sometimes you have a transitive tournament and you took the wrong back edge graph and it has edges. We can still say what it looks like. And what it looks like is a permutation graph. A permutation graph is a graph that you construct by taking a permutation. So here I wrote the numbers 1 through 5. And here I wrote a permutation of them, 2, 5, 3, 4, 1. Guaranteed to be randomly chosen. And the permutation graph has 5 vertices, and the rule is that 2 numbers are adjacent if they're an inversion in the permutation. Or visually, if you draw lines between each number on top and its copy below, then the corresponding vertices are adjacent if the lines intersect. So because the line between the two 1s and the line between the two 2s cross, 1 and 2 are adjacent. But if you look at the 3s and the 4s, those lines don't intersect each other. And so if I drew it right, 3 and 4 are non-adjacent. And these are exactly the back-edge graphs of transitive tournaments, which makes sense, right? It just is the permutation that measures how far you are off from the correct ordering of the transitive tournament. That's exactly the permutation graph you get. But not every graph's a permutation graph, and in fact, permutation graphs are perfect, meaning that their chromatic number equals their clique number as undirected graphs. So that gives us one more fun way to make tournaments with large chromatic number. I promise that's the end of the list. You could say, okay, let's take my favorite graph, just put it in whatever order, and say this is the back-edge graph of some tournament. And that's a way to make a tournament. How do you get it to have large chromatic number? Well, one way you could go about this is you could say take a graph which is triangle-free and has large chromatic number, and those exist. Take some such graph, order it in any way you like, does not matter. Say this is the back-edge graph, these edges go this way, all the others go that way. Now this tournament has large chromatic number, because suppose it doesn't. What does that mean? That means now you have a coloring of the back-edge graph such that each color class is a transitive tournament and hence a permutation graph. But it's a triangle-free permutation graph because I said let's start with a triangle-free graph. And permutation graphs are perfect, meaning when they're triangle-free, they are two-colorable. So any coloring of the tournament you give me, each color class in the back-edge graph is two-colorable as a graph. And so the back-edge graph can be colored in the graph sense with at most twice as many colors as the tournament could. And if you believe me or you followed the inequality along the way, it's the right direction. The chromatic number of the tournament is at least half that of the graph. And half is because the graph had clique number 2. If it had clique number 100, it would be 1 over 100. So that's yet another exciting way to make graphs, to make tournaments with large chromatic number. Which is annoying because then you have to get into what are the graphs that have small clique number and large chromatic number. And that's a whole nother topic that I am not even going to start on. So that's a little bit of a damper on our goal to say when do tournaments have large chromatic number, because turns out we actually have to understand what graphs do. And that sounds like hard work. Fortunately, people came along and invented something else. You know how I keep talking about clique number in graphs and coloring in graphs and coloring in tournaments? And what is clique number in tournaments? It certainly should not be the clique number of the underlying undirected graph, because then the clique number of an n-vertex tournament is n, and that's no good. And so clever people went ahead and said, well, for chromatic number, what worked was saying, let's look at all the back-edge graphs, look at their chromatic numbers, take the smallest one. Why don't we do that for clique number? And that gave rise to a really fun concept. So that is the clique number of tournaments. you take your tournament, you take all the package graphs of it, you compute all their clique numbers, you take the smallest one. Suddenly you have something which is at least non-trivial. Here's a picture of D3 and a drawing that without a doubt will immediately convince you that it has clique number 2. In a graph, if I ask you what causes large clique number, you will probably look at me a bit funny. Right? In a graph, if I want to show you it has clique number 100, I just say, well, here's a clique of size 100, we can both see it. In a tournament, that is not clear at all. If I want to show you a tournament has small clique number, I can give you a package graph with small clique number, and I can say, well, certainly the clique number is no more than this. But if I want to convince you this tournament has clique number 1,000, then we're both out of luck. Right? It is not clear how to do that. Before getting into that, let's first check that this notion makes sense. If you think about normal chromatic number and clique number, there's kind of one inequality that is immediate and is the first thing you will learn. Chromatic number is at least clique number. That's also true in tournaments. Why is that true in tournaments? Well, that's right, it's true for every package graph, in particular for the one that attains chromatic number. And so in that one, we get clique number at most the chromatic number of the tournament, and maybe some other package graph does even better. But that only shifts the inequality in the way that we like. So that's nice. This notion of clique number at least satisfies kind of the very, very basic thing that we want of clique number. And then the same smart people went ahead and said, okay, let's start at one tournament. If I exclude one tournament, when do I get bounded clique number? Turns out the answer is the same as for chromatic number, which is a little bit fun and also a little bit discouraging, because that means maybe we'll run into the same problem of, and now there's all these constructions that we don't understand. But if you exclude one thing, we know the answer for chromatic number, we know the answer for clique number. The answer is heroes both times, which is kind of fun and tells you that heroes seem kind of important. But again, heroes are 2 colorable, and so their clique number is also at most 2. So they still don't tell you what caused the large clique number. I can't show you, here's a hero, that's where the clique number comes from, because it has clique number 2 or 1. As an additional treat in graphs, if you want to decide, does this graph have clique number at most 3? Then you just look at all subsets of size 4 and ask, is this a clique? In general, computing clique numbers can be hard, but if I fix the target clique number, does this have a clique of size 5? That's a question you can answer in polynomial time. Not so for tournaments. Deciding if a tournament has clique number at most some k is NP hard for every k except 1. 1 just means transitive tournament, and that's polynomial time, but anything else is NP complete. So that's a little bit annoying that there's this brand new parameter, it behaves nicely, and we can't compute it at all. We can't even decide, is it equal to 2? The reduction is basically from 2 coloring, which makes a little bit of sense, right? Because a 2 colorable graph is also a graph with clique number at most 2. And so the reduction basically takes advantage of that. And I will not burden you with an NP hardness reduction today, so we're going to skip the rest. But despite those bad news of we can't even tell if clique number is equal to 2, we can actually pinpoint where does large clique number come from. It's actually the two things that you've seen. I showed you two constructions, AN and DN, which are named so by the people who invented them. There are no secret constructions, BN and CN, that I'm withholding. And it turns out, if you exclude AN and you exclude DN, your tournament has bounded clique number. Which is kind of fun for chromatic number as well. Because if you have large chromatic number, you might have AN, which has large chromatic number. You might have DN, which has large chromatic number. Or you have neither, so you have bounded clique number and large chromatic number, which is the third kind of construction I showed you. This is, of course, just punting all the difficulty to the undirected graph case, but we can do that now. It's undirected graphs who are the problem, not tournaments. And I might say a word and a half about the proof, but also it is now after 4 on Friday, so we'll go very light. And in fact, before that, because open problems are fun, I'm going to try and interest you in an open problem. There's a third parameter that I want to mention, which is domination number. Domination number means that you're looking for the smallest set, such that this set plus all its out neighbors are the whole tournament. So in a transitive tournament, a set of size 1 suffices. You just take the first guy, and it's out adjacent to everybody else. In general, though, domination number in tournaments is not bounded. Although it's surprisingly annoying to construct a tournament with large domination number. Nothing I've shown you so far has large domination number. For AN and DN, it's 2 or 3. And it turns out that domination number kind of further completes the inequality, right? We have chromatic number, which is at least clique number, and clique number is at least domination number. If this were 9 in the morning, I would ask you, why is that true? But I sort of vote that we just believe it. And then I thought, maybe we'll do footnotes. I wanted to compare these 3 parameters and what we know about them, and what open questions there are. So right, the first thing I showed you for chromatic number and clique number is, if you exclude just one graph, when is this parameter bounded? And for chromatic number and clique number, the answer was if and only if you exclude a hero. For domination number, it's true if you exclude a hero, domination number is bounded, because domination number is in fact bounded by the other 2 parameters. But there's more. And that's annoying. This is one of the open questions. We actually don't know which tournaments, when excluded, give rise to bounded domination number. We know there are infinitely more than just heroes, but we don't know the complete answer. For chromatic number and clique number, you get that they're sort of local, and there are 2 meanings of local that are a bit different. The first is, if you think about a graph, chromatic number is not local, right? Chromatic number could come from the whole graph, but any little bit you look at. small chromatic number, the neighbors of any vertex might be a stable set, so somehow chasing chromatic number locally is hopeless. But clique number in graphs is very local, because if you have clique number 100, then you have a set of size 100, which has clique number 100, namely the clique of size 100. And so you could ask, what about tournaments? What happens to these kinds of, this parameter is sort of local? And so it lives in the neighborhood of a vertex is true for chromatic number and clique number. For both of them, if you have a tournament with huge chromatic number or huge clique number, you can find a vertex whose out neighborhood has pretty big chromatic number or clique number, which is already not like what happens in graphs. For domination number, you don't get big domination number in the out neighborhood of a vertex for the silly reason that that vertex dominates its whole out neighborhood. But I put it in parentheses because it's still possible that in there somewhere is a tournament of large domination number. If you delete some stuff, that's open. And even more local could be if you have large this parameter, then there's actually a small set that certifies this. And for clique number, we now get this, which is also the case in graphs, right? Because you just, in graphs, take the clique. For tournaments, we know large clique number means you have AN or DN, which is a bounded size set, which certifies here's where the large clique number comes from. For chromatic number, you don't get this because of the other construction, right? I said any triangle-free graph has the back-edge graph. That has large chromatic number. So just start with a graph which is not just triangle-free but has huge girth. Then you can still get huge chromatic number, and any bounded size set, the back-edge graph, doesn't have a cycle, and therefore the tournament is too colorable. And for domination number, this is just open. We do not know. Domination number seems to just be even messier than the other two. But look at that. Clearly this column is the column where things go well. And the proof goes through this concept of mountains, which is common to the chromatic number proof and the clique number proof, which is a bit silly because for clique number you always do get this. For chromatic number you don't always get this. And how a mountain works is basically like AN. In AN we had this clique in the back edge graph, and then for any edge in that clique we had a copy of AN minus 1 that made a cyclic triangle with that edge in the clique. A mountain is a slightly looser version of that. And in the interest of it's Friday, let's skip a few things. One of the things about tournaments I would like to understand more is this concept of bank chains. A bank chain in a tournament means a bunch of sets, and between them the edges mostly go forward, which sounds pretty reasonable. The reason I'm mentioning this is because this seems to be the only tool that kind of robustly gets us from here's a tournament, it's a mess, to here is the right back edge graph. This is the one we want to be looking at. You start with a little bit of the graph where the edges go mostly in the right direction, and then you absorb the rest of the tournament into that. That is the extremely short. I am skipping every detailed version of the proof. You have to first show that you can start somewhere, that you can find a little bit of the graph where most of the edges go from here to there. And then you say, well, now here's this bit where the edges basically all go from here to there. That severely restricts how the rest of the tournament can attach to this bit. If it attaches in a messy way, you get one of the forbidden graphs. So it mostly attaches in a way that looks like all edges go from left to right. Everything else mostly fits into this picture. And I don't know why this is the right method, but somehow this seems to be the right method for here's your tournament, get it in an order that we can make something out of. We're going to absolutely not look at any details, but look at this, it is a bank chain. I feel like I'm legally required to say words about chi-boundedness. So chi-boundedness usually is something we look at in graphs, and in graphs we say, well, you know there's this inequality that the chromatic number is at least a clique number, right? When can we bound it the other way, that the chromatic number, did I say it the wrong way around the first time? I totally did. When is the chromatic number bounded by some function of the clique number? Well, for tournaments, we also get chromatic number is at least clique number, so now the other question makes sense. When is chromatic number bounded by some function of the clique number? And we saw that that's not always true. Via exactly the same as in graphs. You take your favorite graph with small clique number and large chromatic number, you say that's the back-edge graph. We showed this has large chromatic number, it certainly has small clique number because that's literally the back-edge graph you started with. So the class of all tournaments is not chi-bounded, and that means that chi-boundedness in tournaments is a question that seems kind of interesting. And by this same construction, if you take a graph with large girth and large chromatic number, you call it the back-edge graph, you can show that if excluding some tournament gives you chi-boundedness, that tournament must kill off this construction so it cannot have short cycles. So it must have a back-edge graph, which is a forest. And, well, in graphs, we actually think that that's how chi-boundedness works. If you exclude one graph, it has to be a forest, and that's if and only if. Fortunately, in tournaments, that is not the case. There are tournaments that have a back-edge graph, which is a forest, and excluding it still doesn't give you chi-boundedness. So somehow in tournaments, something else is going on. And this seems too much effort for Friday. I'll show you this. One thing that's kind of fun is now you can ask questions of the form, are these kinds of tournaments chi-bounded? And these questions will sound somewhat silly, because one of the questions we looked at is, what about interval graphs? And if you think about graphs, interval graphs are a class that is perfect, so chromatic number equals clique number, which means asking, is this chi-bounded in graphs, is not a very good question because it is chi-bounded in the literal best possible way. They are the best behaved class, a subset of the best behaved class for chi-boundedness. And so we thought, well, clearly that means that's the class we should look at in tournaments. So what I want to do is I want to say, take a bunch of intervals on the real line. How do we turn this into a tournament? Well, let's make it a back-edge graph. Let's order these by left endpoint. And that's the back-edge graph. They are adjacent if they intersect. They're non-adjacent if they don't. So in this picture, for example, red and orange are disjoint, and red's left end is to the left of orange's left end, so that is a forward edge, and all the others go backward. So for example, green and dark blue intersect, and the left end of dark blue is to the left of the left end of green, so that edge goes backward from green to dark blue. which is a class of tournaments that, despite the fact that this was extremely convoluted, actually was already considered by other people, so it doesn't come totally out of the blue. And we showed that these are polynomially chi-bounded, and it turned out that that essentially came down to a result due to two former Waterloo grad students who showed that circle graphs are polynomially chi-bounded. So it's a very Waterloo-themed result. Okay, I think the energy in the room has left. And also, I don't think anybody has eaten whatever this is yet. So let's stop. You're allowed to ask questions, though. That's a good question. It's a bit scary because usually tournaments means we have to think about induced subgraphs, and Rödel's theorem is not true for induced subgraphs.
Most of it goes through okay, except for when the chromatic number is caused by a large cliff.
Mm-hmm.
If your chromatic number of your thing isn't caused by a large cliff, you get it from a graph. Result.
So you're saying if a tournament has large chromatic number, maybe we can find a triangle-free digraph with large chromatic number?
I don't know what I'm just wondering if it's true.
Oh, I don't know if it's true. We haven't thought about it, but that sounds fun.
So you pointed out how the structural problems of forbidding stuff were really hard. Could I ask a slightly different question where I say, can I forbid enough so that like that the growth rate of the number of them is not too bad? Like maybe forbid enough that the number of tournaments forbidding that grows polynomially or something like that? Does that give a nice world to ask questions in?
That's a good question, and I don't know enough about it to give a good answer. For graphs, people have looked at twin width, which is a graph width parameter that seems to correlate with delineating the growth of a graph class. So it's possible that just doing the same in tournaments might work, and maybe people have already done that, but I don't know. Maybe somebody knows.
So if I fix a tournament and I'm looking at all the different back-end graphs for that tournament, if I change the permutation by an adjacent transposition, then it's not going to be too crazy.
Right.
So I could imagine making the Brucha order and like labeling it with the back-end graphs. Does that, and I feel like some of the properties you care about would be fairly well behaved in that process. Does that come up? Does that happen?
I don't know. That seems like a question I need to ask Logan about. Sorry, I've not been able to answer any questions.